Overview for Eclipse 100. The first one is to create the RUNSPEC section and create grid section. The next is create prop section. The third one is initialize the model. And last but not least, set up the schedule session and set up prediction strategy. RUNSPEC session and green section have their own function in Eclipse 100. For RUNSPEC session, the first section, it is the first section for input file that consists of run title, start date and dimensions such as well and number of block. Meanwhile, for the grid section, it is define the grid dimension and petrophysics parameters such as porosity and permeability. For the first section, which is create RUNSPEC session and create grid section, assumption is made. The first one is the reservoir is undersaturated, which is contains oil and water, and the well depth is 2, 3, 2, 1. The explanation for well depth, the 2 or the first number means the number of well which are producer well and injector well. The 3 in the well depth means that the 3 maximum number of grid blocks connected to the well. The 1 assumed to be one type of well within each type of the model. And the last one, the 2 in the well depth, means that the maximum number of well within the group, which are 2 groups, which are oil and water. From the coding, the titles mean the names of case study, while the dimension is the volume of the reservoir in form of cell, which is given in this case study 50 times 15 times 3. The well depth consists of well and group dimension, and the start in the coding means the project kick-off, which given in this case study is 1 January 2019. The grid stands for number of cells which is given, and the tops mean the surface of the reservoir, which is from the top we can see the X and Y cell, and it is times by depth of the top reservoir, which is given 2000 meters. And then the permeability means the permeability of each layer represented by X-axis, Y-axis and Z-axis. Last but not least, the porosity means the porosity of the reservoir, which is given 0.3.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adlan and I will be presenting the prop section for group 1. Now the prop section, or also known as the property section, is the section where the properties of oil, gas and water are presented in the simulation. So let's take a look at the solution and summary. So before we start with the coding for prop section, we have to make a few assumptions which are obtained from the case study. So first and foremost is the SWOF, which means there are only 2 phases inside this simulation, which are oil and water. Next is to determine the type of oil, which is as we have received from the case study, it is stated that this reservoir is an undersaturated reservoir, which means it is dead oil, therefore RS is constant. And the third assumption is CV is equals to 0 due to the nature of dead oil. And now let's move along to the coding. Okay, for the coding lines for the property section, we, as like all other sections, we have to start with props so that it understands. And the first coding line that we see here is density. Now density is where we put in the oil, water and gas densities in the respective order. So 860 is oil, 1033 is water, and the gas density is 0.853. Just for your information, that all values stated here are all in metric. And next is to input the PVT data for oil, and for our case it is PVT data for dead oil, so therefore the first line is PVDO. So the parameters of PVT are introduced as pressure, oil formation volume factor, and viscosity in that order. So as you can see here, 20 is the pressure, 1.25 is the oil formation volume factor, and viscosity is 1. And then we have the parameters at 100 pressure at 100 bar, and then we have parameters and pressure at 400 bar, as you can see. Now moving along to PVTW, which is the PVT data for water. Now water has some additional parameters, which are water formation volume factor, water compression, and viscosity. And as you can see here, the way it is ordered is in pressure, BW, CW, viscosity, and then viscosity. Next we move on to rock, which is where the lines represent the rock parameters. So rock is actually just rock compressibility. So the data is pressure and rock compression, which is pressure at 270 bar, the rock compression is 4.67 times 10 to the power of negative 5. And last but not least is SWOF, which is the water and oil relative permeability. And in this section, they will require 4 sets of data, which is water saturation with its consequent water permeability, relative permeability, oil relative permeability, and as well as capillary pressure. And as you can see here, 0.2 is the SW, water relative permeability is 0.0, and oil relative permeability is 0.9, and the capillary pressure is 0.2721. And that is all from me. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Hi, my name is Amira. I will continue with the Initialize model. To initialize the model, it contributes 2 sections, which are solution and summary section. Okay, so the coding begins with the solution keyword. Solution section is a specifications of initialized conditions in reservoir, which might include several variables, for example, pressure, saturations, and compositions of every grid block in the reservoir. The pressures and saturations are then computed by Eclipse by using data entered with the equal keyword. The data extracted based on the given case study is summarized as follows, where the initial pressure is set at 270 bar at a depth of reservoir top 2000 meter. The all water contact, or WC, is below the reservoir, which is at the depth of 2560 meter with 0 capillary pressure at the contact. Then the initial solution may be read from a restart file created by an earlier run of Eclipse. Restart file is entered using the rptst keyword. If set to 3, the restart files are created every NTH report time. The frequency of the restart is governed by the mnemonic of frequency equals to n. Next, the coding continued with the summary section. Summary section is a specifications of data to be written to the summary file after each time step. The request data keywords that are specified in summary section are shown as follows, which includes the field average pressure, bottom hole pressure, field oil production rate, field water production rate, field liquid production rate, field water injection rate, field water injection total, total field water production, total field oil production, field water cut, reservoir volume production rate, reservoir volume injection rate, and also oil recovery factor.
My name is Harith by Aimiros, and next we'll be move on to schedule and prediction strategy setup section using Eclipse oil and gas simulation software. Schedule and prediction strategy are important to identify the pattern and the result from the specification and parameters of the well from the previous coding. To run the setup, first the coding is set to schedules. The schedule section specifies the operation to be simulated, which is the production and injection controls and constraints, and the times at which output reports are required. Next, RPTRST. This coding controls on output to the restart file, and then the coding continue with basic equals to 2. If the output basic restart file is set to 2, restart files are created at every report time until this switch is reset and are all capped. To move on with the simulation of the schedule, well specs is written. Wells can be introduced at any time in the simulation, but once a well has been introduced using the keyword well specs or well spec L, its connection properties and operating status must be defined. Okay, to continue with the coding of well specs, well name template, well list or well list template, and then followed by as stated at the coding, which you can see the prod G1 introduce the well name and well name template with the location of the connecting grid blocks. Next, the coding continue with comdat, which defines the connection between wells and grid blocks. This keyword is compulsory to the coding. Next, for the parameters of the well is stated, which is the well is in open condition, and then the diameter of the well and the connection is stated from the coding. To continue with the coding, either wconprod or wconhist based on the setting of the coding, which is for this case is scheduling and not history. wconprod is used. wconprod is used to specify production wells once they have been introduced with the well specs and the comdat from the coding. Next, the specification of the production stream stated for the group 1, which is the liquid production rate, stated with open with 100 meter cube per day and water hole pressure limit of 9.308 bar from the case study. Next, wconinj is the control data for injection wells. For this case, wconinj is used rather than wconinjh due to the prediction or strategy rather than the history for the coding section. The specification of the water injection stream are stated with open with rate of 150 meter cube per day and water hole pressure limit of 680 bar based on the case study. At the ending of the schedule and prediction strategy setup, tuning coding is stated for this coding to determine the time step and convergence control of the well. Based on the case study, it is required to run the data 50 times. Hence, the T-step coding are used to advance the simulation over specified intervals between the reporting times, which is 50 times for 30 days. And then to end the simulation, the coding N is to terminate the simulation. Thank you, that's all from me.
From the graph plot of field liquid production rate, field water cut, and field oil production versus time, it was observed that as water is injected at 150 meter cube of water per day, the oil and liquid production will also drastically increase, even when the liquid production at 100 meter cube liquid per day. Since water injection rate is 15 meter cubes per day more than the liquid production, it is expected to see drastic increase in water cut. Thus, at the time between 60 days to 70 days, the water cut will exceed field oil production. As conclusion, as water cut increases, the oil production decreases over time. The field reservoir production rate FVPR can be calculated by using the formula above. It was determined that the injection at reservoir condition is higher than the rate of surface injection. If the rate of produce is more than what it was compensated, there will be a reduction in pressure since the volume occupied by the surface injection fluid is not enough to fill in the gaps left by produced fluid. Over time, from the graph curve, the reservoir production will tremendously increase until the 80th day. Then, the production will remain stagnant to ensure the field volume production rate FVPR does not further decrease lower than that of 115.533 meter cubes per day. If the FVPR further drops, the FWIR will need to be increased as well to maintain the pressure. As observed, the field water cut FWCT does not immediately increase after the 80th day, where the FPR remains stagnant or in control level. Instead, it increases gradually and slowly until it reaches FWCT at maximum capacity at 1280 days. From the graph above, it can be said that the average pressure of the reservoir is dependent on the field water injection and field oil production rate. In this case, the field water injection and the field oil production are almost the same, where it peaks at the start to the 80th day, where both wellhead pressure for the water injection and the oil production are kept at constant. The pressure drop in the wellhead is expected to increase for the first 80 days and decrease after the 80th day. From the graph above, it was observed that the bottom hole pressure of water injection and production well starts at different pressure. Water injection bottom hole pressure starts at 279 bar, while the production well bottom hole pressure starts at 262 bar. The trend that seems particular in this is that the water injection bottom hole pressure, the trend fluctuates upwards in the first 5 hours, and then slightly pressure drops for another 5 hours before gradually increase constantly until the 10th day. This trend is also particular for the production well bottom hole pressure. The trend line fluctuates downward in the first 5 hours and then gradually increase constantly until the 10th day. This phenomenon can be identified as the pressure waves that travel in the reservoir at velocity controlled by the hydraulic diffusivity. Hydraulic diffusivity is the measure of diffusion speed of pressure disturbances in groundwater level. Large values of hydraulic diffusivity lead to fast propagation of signals in aquifer. For the graph findings above, the fast propagation signal, which is less than 5 hours, means the hydraulic diffusivity in this reservoir is quite high.